Well, there's a relationship between acceleration, speed, and curvature. If r of t is a position vector for a smooth curve C, then the acceleration vector is given by, acceleration is d squared s over dt squared times the unit tangent vector. That would be the second derivative of the arc length with respect to t, plus kappa the curvature times the square of ds dt times the normal vector, unit normal vector, where k is the curvature and ds dt is the speed. So this is the speed squared. This is the first derivative of speed. So here's an example. Use theorem 12.10, that's this one, to find the tangential and the normal component of acceleration for r of t equal t squared I plus 2tj plus t squared k. Well, the velocity vector, that's easy. The derivative of this is 2t. The derivative of this is 2. The derivative of this is 2t. So there's our velocity vector. Easily converted to a unit tangent vector by dividing by its length. The length of this vector would be the square root of 2t squared plus 2 squared plus 2t squared. So in other words, it's going to have like 8t squared plus 4, and then we could factor the 4 out of that, and the square root of that 4 is 2, so 2t squared plus 1 is what doesn't factor out of the radical, and then this is just our velocity vector itself. So there's our unit tangent function, and t prime of that would be the derivative of that thing. And so we can go one piece at a time. This one will require the quotient rule, and trust me that these are correct. The derivative of this one over here, well, hey, that'll require, well, when I do down d up, I'm going to get a 0, so therefore that, I hope you can see where that part came in there. And here's that whole vector. So it's like, if you want to think of it as down d up, here's the d up. So you know, this down times this d up, and the half is actually this too, and then plus this up, and then this d down. So there's that part. That's the derivative of this function. So, ugly as it may be, there it is. So, that would be our vector simplified. And let me see why it simplifies like that. Because if we find a common, well, trust me, I think I'm going to use my software to do that. I would. You could probably see where I need to multiply this to get a common denominator. I need to multiply this fraction by 2t squared plus 1, numerator and denominator. Then it would have a common denominator, but what happens is a lot of things then simplify, or at least I hope that's the case. So, the length of our t prime of t is this, the length of this vector, which is the square root of each of the component functions divided by this squared, right? So 1 squared and a 1 squared and a 2t squared, negative 2t squared actually, divided by this squared. So there's that. Squaring that just drops off the 2. And so we wind up with this function, 4t squared plus 2 divided by 2t squared plus 1 cubed. And all that's under a radical. So now ds dt, you have to go back for a ways, is the length of the velocity vector, and the velocity vector was found, where was it? Way back here. Okay, so the length of the velocity vector, I think we already have that one down. yes, the square root of 2t squared plus 2 squared plus 2t squared, which simplified as 2 times the square root of 2t squared plus 1, because it's really 8t squared plus 4. Factor out the 2, and you should be able to follow that all right. Then the second derivative, take the derivative of this function, we multiply by 1/2, and then we subtract 1, and then we multiply by the inside function's derivative, which is 4t. You probably can see where that came from pretty easily. The 1/2 cancels out the 2 that was here. And so our tangential component of the acceleration vector from this nice theorem, there it is. Okay. And I guess for us to find the normal component, that's going to be a curvature times the square of that velocity vector, which we already have, times the unit normal vector. So we need to find that part, and that means that the curvature is necessary. Well, that's the length of t prime of t over length of r prime of t. Here's the t prime of t, or the length of t prime of t, and the length of r prime of t. I've got to go back for that one. That'd be the length of this one. We already have that. So yes, there, I knew we already had that. There it is, divided by the length of this vector, which we already worked out once. So this big expression, which simplifies into this smaller expression, square root of 2 over 2 times t squared plus 1 to the 3/2. If you take the time, you can probably figure most of that out. If you look at this, this is twice 2t squared plus 1, so one of those, this one cancels with one of these, but the square root doesn't cancel. And so the other 2 that were here, since it's a square root, they would move to the denominator, and we get to the 3/2. This 2 remains here. This 2 that factored out of this is the square root of 2 that remains. So there's our curvature, and so we want that curvature times ds dt squared, the speed squared, and I thought I had that somewhere. Here it is. This is the ds dt, but we want to square that, and that would get rid of the radical, would make it 4 times 2t squared plus 1. So it's this that we just found, the curvature, times this squared, which is 4 times 2t squared plus 1. There's the 4, there's the 2t squared plus 1. Here's the square root of 2 from this part. Here's the denominator from this part. And when you simplify all that, what happens is this cancels with part of this one, right? Since that's the 3/2. The 4 and the 2 cancel. We get 2 square roots of 2 over the square root of 2t squared plus 1. And I can't help but wonder if one of the other curvature formulas would have been easier to use, because that was painful.